Hello, welcome back. So these are the free physics classes through YouTube channel. So today I'm going to discuss Schrodinger wave equation. So what is the uh, necessity of a Schrodinger equation? Before entering to Schrodinger wave equation, we need to discuss about the classical mechanics of wave equation. So we know the classical mechanics. A wave equation is a second order differential equation in space and time. The solution of this equation represented wave disturbances in a medium. So therefore, here I'm going to represent this mathematical wave equation. So for example, in classical wave, okay, this classically a wave represented by a function, right? F of x comma t in case if it is one dimensional, or else we can represent it in the position like this, right? R comma t, because if you consider the three-dimensional object. So this function, the mathematical representation of wave in classical form, this function is there, right? So it must be satisfy this equation, the second order differential equation, especially in the that is in space and time. Okay, so both space and time, which means this space is second order differential equation, second order term, and time also that is a second order differential term. Okay, this type of equation. So we already know these are all equation, the wave equation, the classical wave equation represented like this. So dou square f divided by the x square, right? Minus 1 divided by v square. So dou square f divided by dou t square. Here the v is the velocity of a wave. So sometimes we can use here c, the light velocity of light. So the wave, we know the wave properties are lambda and frequencies. Therefore, the mathematical solution of this equation, I'm going to write like this. So we already know this one, f of x comma t equal to a e power I is kx minus omega t. So this k x minus omega t. Okay, here k is the propagational vector, omega is the frequency, right? So therefore, here I'm going to uh, substitute this equation. This is solution, right? So maybe you can take this one equation number one. You can take this one equation number two. In case if you try to substitute this equation, the solution equation here, the second order space derivation, second order differential equation in time also, so we can get the equation like this, which means uh, so 2 times, in case if we derive 2 times, right, this one 2 times derivative with respect to x. So I square minus k square. First one is minus k square minus 1 divided by v is there, already 1 divided by v square, and remaining this part dou square f divided by dou d square. I want to differentiate this thing to 2 times with respect to t, then I can get the answer with respect to t, right? So minus into minus plus, okay, then I is there, I square minus, then I can get minus 2 times omega square, okay. So this one is minus omega square, that equal to 0. So therefore I can write this equation like this. So omega square equal to v square k square, or I can omega is proportional to k. So we know the frequency and the propagation vector relation. That we can call these equations dispersion relations. Dispersion relation. Okay. Generally, we can observe this dispersion relation in solid state physics. That is monatomic lattice vibration, diatomic lattice vibrations. There we can find easily this dispersion relation. Propagation of a wave in a medium, right? So this is the dispersion relation. So here I consider the particle, whatever particle is there, that particle here I am considering, that is a free particle. A free particle means that the force free particle, which means there is no potential energy. Then we have only the kinetic energy. We are familiar this type of equation, p square divided by vm, right? Then uh, then I can get that dispersion relations, right? So in case this plane wave is correct description of free particles, so this must be satisfy this equation, right? So then I can get this one. So omega is proportional to k square. So whereas come to this quantum case, so we know the quantum mechanics, we can represent it energy E equal to E equal to E equal to h nu, right? So then E is proportional to frequency, or we can represent it like this: E is proportional to so this frequency. Then and so how we can get this one? So E equal to h nu, right? And then this nu can be expressed in terms of frequency, the angular frequency divided by 2 pi. So this is h cross h divided by 2 pi is h cross. We already know that thing. So therefore, the h cross omega. This is the relation. Okay, the h cross omega. So then here the de Broglie wave equation P is equal to h divided by lambda, right? So then we can represent this h divided by 2 pi into 2 pi divided by lambda. Then P is equal to h cross k. This is another equation. So here P is proportional to k. Yes, if you observe clearly here, here E is proportional to omega, P is proportional to k, but E equal to p square divided by 2m. Then in case if you try to substitute this p square value and e value, then you can get this equation. See here, what is e? H cross omega, h cross omega, right? At equal to what is p? H cross square divided by the h cross square, k square, k square divided by 2a. So in case if you neglect this constant, well, then I can write like this equation: omega is proportional to k square. So if you observe here clearly, in case if I try to apply this classical wave equation, so in terms of the free particle energy is equal to p square divided by 2 pi. So then I get the current dispersion relation of this equation: omega is proportional to k. Whereas it comes to the quantum cases, I get the dispersion relation, um, uh, omega is proportional to k square. So initially we start with some classical equation, then we can get two type of dispersion relations, right? So this is the wave represented in classical mechanics. So this is the wave represented equation, dispersion relation in quantum mechanics. So we need to this type of a dispersion relation for the particle exhibit the wave nature. So then they try to solve the differential equation. So in terms of I mean, time is a single derivative and space is double derivative. So they want this type of differential equation. So to satisfy omega is proportional to k square dispersion relation. So what I mean that dou by dou t, this time is single derivative and the space is double derivative. Okay, space is dou square divided by dou x square. Here some constants are there. No need to worry about that. This type of equation they want. So in case if you try to solve this equation, we need to get this type of dispersion relation. So here I'm going to show you that thing. This derivation actually my professor told the f equal to f of x comma t, so free particle dispersion e power I the kx minus omega t, right? Kx minus omega t. So we need to get this type of dispersion relation. So in case if you try to assume this one here dou by dou x, I want this type of equation, right? See here, this is some constant c dou square f divided by dou x square, dou x square. This is one important equation. So in case if I try to substitute the solution f of x comma t in this differential equation, first order in time, second order derivative in space coordinate other, then I can get here. See here, in case of you can derive with respect to time, one time, right? Minus is there, minus omega we can get here, minus I omega, and the remaining what is e power, I mean a, some included also there here, a e power I kx minus omega t equal to, here the double derivative is there, some constant is there, c is there. With respect to space, we can derive this function into two times, right? So with respect to x minus is there, then we can get here the minus k square a e power I kx minus omega t. So these are all cancelled. Then I can get I omega equal to c k square. So this is the required dispersion relation uh, to describe the uh, wave nature of the particle. Okay. So then the Schrodinger tried to derive the equation, this type of equation. In case if you try to find this C, I'll show you how to find that C. Uh, you can use E equal to P square, E equal to P square divided by 2m, and we know E can express in terms of H cross omega, then uh, P equal to uh, H cross square K square divided by 2m. Okay, then we can get here omega equal to H cross K square divided by 2m. So by using this equation and this equation, so by using these two equations, I'm going to try to solve this C value, right? So here C equal to I omega uh, C divided by, then you can substitute so omega equal to C divided by 1 divided by C, right? From this equation, omega equal to C divided by I K square. From this equation, omega equal to H cross K square divided by 2m. So then C equal to, from these two equations, C equal to, we can get the I H cross divided by 2m. So therefore, here the C is there. So we can get those dou by dou t equal to, what is C value? I H cross divided by 2m, this function, right? Dou square f divided by dou x square. So this is actually the Schrodinger wave. This is actually the Schrodinger equation they got. So here I'm going to say one thing. What exactly I learned during this course. Uh, so this is not exactly way of derive Schrodinger equation. We can derive in another way. So for understanding purpose, why Schrodinger equation required in quantum mechanics especially. So in most of the classical cases, in case of electromagnetic theory, classical mechanics, wave equation generally we can observe this type of equation. Okay, dou square f divided by dou x square minus 1 divided by v square, dou square f divided by dou t square is equal to 0. So whereas comes to the uh, quantum cases, then we can represent it a wave equation, Schrodinger wave equation, right? So these are the reasons why we require this Schrodinger equation. Both are correct, but so the wave associated particle. So I can say that incorrectly. So the differential equation for the wave associated with the particle in motion, so that cannot be derived from the classical forms, right? So because this classical transformation equations, wave equation, according to with the wave property of matter, that based on the de Broglie hypothesis, this entire derivation is based on this uh, de Broglie hypothesis, right? Lambda is equal to h divided by p. So this de Broglie hypothesis. So here we need to modify this equation like this. Okay, we can get the Schrodinger equation. Okay, so this is how the we can get the Schrodinger equation, and we are going to derive the original Schrodinger equation. So we already know this is the exactly a reason to derive the Schrodinger equation. So now I am going to derive the Schrodinger equation. So this is all about the why we deriving Schrodinger equation. What is the reason behind the Schrodinger equation? So we need one differential equation. It satisfies the dispersion relation that omega is proportional to k square. This dispersion relation. Okay. So we need the that wave differential equation for the wave associated with the particle in motion. Okay, that is exactly uh, time is single derivative, space is double derivative. Okay? This type of dispersion relation, sorry, this type of wave equation we need to satisfy. I mean to explain the wave associated with the particle matter wave. So now I am going to tell the Schrodinger equation. That is very easy, one-dimensional Schrodinger wave equation. So let us consider the particle of uh, moving with velocity v. So then we can represent the total energy of the particle E equal to p square divided by 2m plus potential energy. Okay. So if the motion of the particle due to the action of force f of x, so which is a function of x, so this motion is acting on f of x. Then the v will be the function only the x, right? So I'm going to multiply this equation. This equation number one. I'm going to multiply this equation like this. P also I'm going to denote here, which means the momentum in only x direction. P square divided by 2m wave function psi plus v wave function psi at equal to this. So this is a differential equation, right? So this is a differential equation. The solution of this differential equation, the wave function psi equal to the a e power I h cross px into x direction et. This is the uh, solution of this differential equation. Then you can try to substitute this differential equation here. Uh, so in case if you try to solve this equation, so I'm going to, this is equation number 3. So I'm going to differentiation with respect to x equation number 3. So first time the dou by dou psi divided by dou x equal to, so this is a, okay. So here I h cross is there. This is just derivation. Okay, no need to worry. Px x with respect to x, right? The remaining thing is I h cross divided by px et. Okay, therefore this equation I'm going to arrange like this. P of x a e power a also there here, yeah, here also there, I divided by h cross px minus et. So then we can get the another time the differential equation. Then this is wave function psi, right? So I h cross divided by px, this wave function. Then in case if you try to solve the second time the differential equation, if you apply this one, then you can get this here the minus 1 divided by h cross square uh, p squared psi, p squared psi. Therefore here I'm going to write this p square like this equation. P square wave function psi equal to minus h cross square dou square psi divided by dou x square. So this is one step, the first step, and the second step I'm going to do same thing. This equation, equation number 3, I'm going to differentiate with respect to time, just one. So in case if I try to differentiation equation number 3 with respect to time at single time, equation number 3, you can differentiate with respect to uh, time. You can get this one easily. Uh, so A, I divide by h cross, so minus e power I divide by h cross, tx minus et, right? So after get e power x, in terms of t, right, minus t, and this is the constant value. Okay, then so this is all the wave function psi. So therefore I'm going to write like this: minus I divided by h cross e psi. Then I want to e psi here, from e psi equal to minus h cross divided by I the square psi divided by the t square. Sorry, only t, not t square. So this is second one. If you observe here, the first second equation, p square psi is there, e psi is there. In case if you try to put these two equation, you can get the Schrodinger equation easily. So minus h cross square divided by 2m the square psi divided by the x square plus p psi equal to minus h cross divided by I. After substituting, you can get this equation. So this is a Schrodinger wave equation. Then we can arrange this Schrodinger equation according to textbooks, right? So this Schrodinger equation first derived by 1926. So Schrodinger only 1926, the Schrodinger derived this equation. Then we can write this equation. So this is delta, right? I can rearrange this one. Delta square wave function psi plus 2m divided by h cross square. This is E energy, right? E minus V wave function psi equal to 0. This is the Schrodinger time independent wave equation. Schrodinger time independent wave equation. So this is all about the derivation of Schrodinger wave equation. Next class, I'm going to apply the Schrodinger wave equation to different type of one-dimensional object, and I'm going to try to solve the eigenvalues and eigenfunctions of one-dimensional problems. So simply, I'm going to use the Schrodinger equation to different type of potentials. Uh, First, I'm going to derive maybe the infinite potential well. We are familiar with that infinite potential well. So one-dimensional box, finite and infinite, and a three-dimensional box, harmonic oscillator. So what are the application by using this Schrodinger equation? Next class, I'm going to solve one by one the problems. So one is a particle. One is a First one is a particle in one-dimensional box. Second one is a particle in three-dimensional box. Third one is a harmonic oscillator. Fourth one is the reflection at the step potential. And fifth one is transmission across a potential barrier. So different type of potentials are there. We need to calculate the eigenvalues and eigenfunctions of different type of potentials. This is all of this first chapter.